Circuit protection, specifically Section 240.21, addresses the requirements for protecting electrical circuits. Section 240.21 states that branch circuit protection is needed at the point where the circuit conductors receive their supply. For this scenario, the distribution block acts as that supply point. Section 240.21 C6 mandates branch circuit protection for feeders that supply motor loads. Section 240.21 for exception no. 4 makes allowances for tap conductors if they are protected by an overcurrent protective device whose rating does not exceed the ampacity of the tap conductors. Now, let's apply these concepts to the situation at hand. All the motors are rated at 2 horsepower or less, which generally places them within a 15 amp load requirement. The 12 American wire gauge THHN conductors used possess an ampacity of 25 amps. The 10-foot, 25-foot, and 50-foot feeders are currently protected by 60 amp fuses located at the distribution block. However, the 100-foot feeder might experience excessive voltage drop if protected by the same 60 amp fuse. Considering the need for individual fusing at each motor, for the 10-foot, 25-foot, and 50-foot feeders, individual fusing is not necessary. The 60 amp fuses at the distribution block are sufficient for protecting the tap conductors and the motors themselves. However, for the 100-foot feeder, individual fusing may be required, but only to address voltage drop concerns. It would not provide additional protection to the motor itself beyond what is already provided at the distribution block. In conclusion, individual fusing is not required at each motor for the 10-foot, 25-foot, and 50-foot feeders. Nevertheless, a voltage drop calculation should be performed for the 100-foot feeder to determine if individual fusing is required to comply with the National Electrical Code. To elaborate further, let's delve into the National Electrical Code, or NEC, and examine the specifics of motor feeder protection, tap rules, and voltage drop calculations. The NEC is a comprehensive set of standards designed to ensure the safe installation of electrical wiring and equipment. Understanding these regulations is crucial for any electrical installation, especially in industrial environments where motor loads are prevalent. We have the 60 amp fuses, which are located at the distribution block in the main panel. These fuses provide overcurrent protection for the 10 motor feeders. The motors are 2 horsepower or less. This is a key piece of information because it allows us to estimate their full load current, or flow. For small motors, the NEC provides tables that list the FLA based on horsepower and voltage. Assuming these motors are operating at a common voltage, such as 230 volts, we can find their approximate FLA from the NEC tables. Since the motors are 2 horsepower or less, their FLA will likely be below 15 amps, as previously stated. The 12 American wire gauge THHN conductors are run to all motors. THHN is a common type of insulated wire used in electrical installations. The 12 American wire gauge THHN has an ampacity of 25 amps. This means it can safely carry up to 25 amps of current in typical conditions. Each motor has a line of sight to the panel. This detail can be relevant for certain NEC requirements related to disconnecting means, but it does not directly affect the overcurrent protection or tap rules. Each motor has its own disconnect and fusing at the motor. This is an important safety feature that allows for the motor to be isolated for maintenance or in case of a fault. The presence of local disconnects and fuses at the motor does not negate the need for proper feeder protection. Now let's consider the tap rules. Tap rules are specific provisions in the NEC that allow conductors to be tapped from a larger feeder without having overcurrent protection at the tap point, provided certain conditions are met. The sections 240.21, C2, 240.21, C6, and 240.21 both address different aspects of tap rules. Section 240.21 C2 generally requires overcurrent protection where the conductors receive their supply, as mentioned before. This is the distribution block. Section 240.21 C6 pertains to feeder taps for motor loads. Section 240.21. Overcurrent is an exception that allows for tap conductors to be protected by an overcurrent device rated not more than the ampacity of the tap conductors. Now let's examine the application to the specific situation. The 10-foot, 25-foot, and 50-foot feeders are protected by 60-amp fuses at the distribution block. The 12 American wire gauge conductors have an ampacity of 25 amps. Since the 60-amp fuses exceed the ampacity of the 12 American wire gauge conductors, the tap rule in 240.21 BOMFA cannot be applied without further analysis. To comply with the NEC, the overcurrent protection must be sized appropriately for the conductor ampacity and the motor load. In this case, the 60-amp fuses are likely too large for the 12 American wire gauge conductors and the 2 horsepower motors. One solution is to provide supplementary overcurrent protection at the tap point, such as fuses or circuit breakers, that are sized at or below the ampacity of the 12 American wire gauge conductors. Another solution is to use a different tap rule that allows for larger overcurrent protection, but this would require careful consideration of the motor's full load current and the conductor's ampacity. For the 100-foot feeder, voltage drop becomes a significant concern. Voltage drop is the decrease in voltage along a conductor due to its resistance. Excessive voltage drop can cause motors to overheat, operate inefficiently, or fail to start. The NEC recommends limiting voltage drop to 5% for motor circuits. To determine if the voltage drop is within acceptable limits, you need to perform a voltage drop calculation. This calculation takes into account the conductor length, conductor size, conductor material, current, and voltage. There are online voltage drop calculators and formulas available to assist with this calculation. If the voltage drop calculation reveals that the voltage drop exceeds 5%, you have several options. Firstly, you could increase the conductor size to reduce the resistance. Secondly, you could reduce the current by using a more efficient motor. Thirdly, you could provide supplementary overcurrent protection closer to the motor to reduce the length of the feeder. Now, let's address the question of whether individual fusing is needed at each motor. For the 10-foot, 25-foot, and 50-foot feeders, individual fusing at each motor is not strictly required by the NEC, provided that the tap rules are met. However, it is generally good practice to provide local overcurrent protection at each motor for enhanced safety and protection. This can be achieved by installing fuses or circuit breakers at the motor disconnect switch. For the 100-foot feeder, individual fusing may be required to address voltage drop concerns, as we discussed earlier. The individual fusing would not necessarily provide additional protection for the motor itself, but it would help to ensure that the voltage at the motor terminals is within acceptable limits. In summary, individual fusing at each motor is not always required by the NEC, but it is often recommended for safety and performance reasons. The decision of whether to provide individual fusing should be based on a careful consideration of the tap rules, voltage drop, and motor protection requirements. To ensure compliance with the NEC and to provide the best possible protection for your motor circuits, it is recommended to consult with a qualified electrical engineer or electrician. They can perform the necessary calculations, assess your specific situation, and provide tailored recommendations. Here are some additional factors to consider. The type of motor being used is important. Different types of motors have different starting currents and operating characteristics. The NEC provides specific requirements for protecting different types of motors. The ambient temperature in the area where the motor feeders are installed affects the ampacity of the conductors. Higher ambient temperatures reduce the ampacity of conductors. The presence of harmonics in the electrical system can affect the performance of motor circuits and the sizing of overcurrent protection. Harmonics are distorted waveforms that can cause excessive heating and equipment malfunction. The coordination of overcurrent protection devices is essential for ensuring that faults are cleared quickly and safely. Coordination involves selecting overcurrent devices that will trip in a specific sequence to isolate the fault and minimize the impact on the rest of the electrical system. Finally, always refer to the latest edition of the National Electrical Code for the most up-to-date requirements and guidelines. The NEC is updated every 3 years, so it is important to stay current with the latest changes. By carefully considering all of these factors and consulting with qualified professionals, you can ensure that your motor feeder circuits are safe, reliable, and compliant with the NEC. Always remember that electrical work can be dangerous, and it should only be performed by qualified individuals who are familiar with NEC and proper safety procedures. Now let's focus specifically on voltage drop calculations. Voltage drop is a critical factor to consider when designing motor feeder circuits, particularly for longer runs like the 100-foot feeder in the described scenario. Excessive voltage drop can lead to a variety of problems, including reduced motor performance, overheating, and premature failure. The NEC recommends limiting voltage drop to a maximum of 5% for motor circuits. This means that the voltage at the motor terminal should not be more than 5% lower than the voltage at the source. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times K times I times D divided by Cm, where K is the direct current constant, which represents the resistance of the conductor material. For copper conductors, K is typically around 12.9 ohms per circular mil-foot. I is the current in amps. This is the motor's full load current, or FLA, which can be found in the NEC tables. D is the distance in feet. This is the one-way length of the feeder conductor. Cm is the circular mils of the conductor. This is a measure of the conductor's cross-sectional area. You can find the circular mils for different conductor sizes in the NEC tables. Let's apply this formula to the 100-foot feeder. Assuming the motor has a full load current of 15 amps, the conductor is 12 American wire gauge copper with a circular mil area of 6,530, and the direct current constant K is 12.9 ohms. The voltage drop would be 2 times 12.9 times 15 times 100 divided by 6,530, which equals approximately 5.93 volts. If the supply voltage is 230 volts, the percentage voltage drop would be 5.93 divided by 230, which is approximately 2.58%. In this case, the voltage drop is within the NEC recommended limit of 5%. However, it's important to note that this is just an example. The actual voltage drop may vary depending on the specific motor, conductor, and installation conditions. If the voltage drop calculation reveals that the voltage drop exceeds 5%, you have several options. Firstly, increase the conductor size. This will reduce the resistance of the conductor and lower the voltage drop. For example, you could upgrade from 12 American wire gauge to 10 American wire gauge, or even 8 American wire gauge. Secondly, reduce the current. If possible, try to reduce the motor's full load current by using a more efficient motor or reducing the load on the motor. Thirdly, shorten the feeder length. If feasible, try to shorten the length of the feeder conductor. This will reduce the distance that the current has to travel and lower the voltage drop. Fourthly, increase the supply voltage. Increasing the supply voltage will reduce the percentage voltage drop. However, this may not always be practical or feasible. Finally, use a voltage drop calculator. There are many online voltage drop calculators available that can help you quickly and easily calculate voltage drop. These calculators typically take into account the conductor size, conductor material, current, voltage, and distance. In addition to the voltage drop calculation, it's also important to consider the voltage drop limitations specified by the motor manufacturer. Some motor manufacturers may have more stringent voltage drop requirements than the NEC. Always refer to the motor manufacturer's specifications for the most accurate voltage drop information. Remember that voltage drop is just one factor to consider when designing motor feeder circuits. You also need to consider the conductor ampacity, overcurrent protection, and other safety requirements. By carefully considering all of these factors, you can ensure that your motor feeder circuits are safe, reliable, and compliant with the NEC.